So, remember when math was just about numbers? Those were good days. We had good old addition. We would take two numbers, 4 and 21, and then we would add them. And so we just start, let's say, at the bigger number and count up 4, 22, 23, 24, 25, and we get 25. With this operation that we call addition, we had something called an additive identity. Now we didn't really care to call it the additive identity because it felt like it was overcomplicating everything, and we felt like all those sections of the book that would talk about the additive identity and commutivity and all those things were just adding labels to things to just overcomplicate stuff. But as you go further in math, you realize it's kind of important to call these things something. So the additive identity is that thing for which we add to any number, let's say again 21, and we get back just 21. Well, that means a has to be 0, so that's our additive identity. Okay, we have another thing that we can do with any real number. We can multiply them. So let's say we have 2 and 14. Then we get 28, right? Well, we also have a multiplicative identity, so that 1 times 14 is just 14. So that's our multiplicative identity, it's just 1. Okay, so this is when life was good and we had just numbers. Now we have matrices, and we want to know, is there such a thing as a multiplicative identity for matrices? And why do we want to know? Just trust me, it's important. It really has to do with how do you solve systems of equations, and it becomes a very um, efficient way of looking at things, for lack of a better way of putting it. So let's consider only the n by n matrices. I need something that will take this 1, 4, 6, and 21 and give me back what? Well, let's go back to the additive identity. I added something to 21 and I got just 21. I got what I started with, or what I was, it didn't change that number. So I need something to multiply this and not change it. 1, when I multiplied it by 14, didn't change 14. If I think about matrix multiplication and how it works, what I'll get is 1, 0, 0, 1. So if I multiply this by this, I'll get 1 times this. 1 times this is 1, and then the other thing is 0, so I'm just left with 1. And then this row times this column gives me 1, and 4 is just 4. Now I got to do this. Well, 0 and 1 is 0, and then 1 and 6 is 6. And then same thing, I get 21. So we did matrix multiplication last time, and so I went through it kind of quickly, but you could see it didn't change anything. So at least for, and I shouldn't have said n by n, I should have said 2 by 2. For 2 by 2 matrices, the multiplicative identity, which I'll call I, is 1, 0, 0, 1. Okay, let's look at 3 by 3 matrices. Let me do 1, 2, 3, 4, 5, 6, 7, 8, and 9. Well, similarly, we're going to get 1, 0, 0, 1. But then we got to add something else onto that. The last row is going to be all zeros and a 1, and the last column will be all zeros and a 1 for the third column. So same idea. This entire row multiplies this column, and what do I get? I get 1, and then times the second column, I'll just get 2 and 3. And then this row times this column will give me 4, 5, and 6. Last row times all three will give me 7, 8, and 9. And you can work it out. 1 times 1 is 1, and then the other two numbers are going to be 0. 1 times 2 is 2, and the other two numbers are going to be 0. 1 times 3 is 3, and then 0 times 6 is 0, 0 times 9 is 0. So you just, so you only end up with this top row. I'm sorry if I did that too fast. I'll do more examples. Let's do the second row together. 0 times 1 is 0, 1 times 4 is 4, and 0 times 7 is 0. So here, that's where I get the 4 from. 0 times 2 is 0, 1 times 5 is 5, and 0 times 8 is 0. So I get the 5. So the multiplicative identity, this is our I, it looks like that. So for any n by n matrix, or otherwise called a square matrix, our multiplicative identity is going to look like this. 1s on the diagonal and 0s everywhere else. Okay? This will be the identity. And then we just call it I. Okay? So, let's do maybe another example, hopefully. Yeah, let me jump down to the bottom of this page first. This is on page 485. It's just saying do this matrix multiplication. So again, this is our identity for 2 by 2 matrices. If we do the multiplication, we would get this times this would give me 1 times 3 is 3, plus 0 times 4 is 0. And then 1 times negative 5 is negative 5, plus 0 times 6 is 0. 0 times 3 is 0, plus 1 times 4 is 4. 0 times 5, negative 5 is 0, plus 6 is 6. 3, negative 5, 4, and 6. Okay, that's how it works. I went a little fast with the other example, and I'm sorry about that. Now this is kind of odd. It looks like this shouldn't work because this has got 3 rows, 3 columns. This has only got 3 rows and 2 columns, but this actually will not change. This I will not change this matrix here, and we'll work it out. So 1 times 5 is 5, plus 0 times 2 and 0 times 6, so you just end up with the 5. 1 times negative 7 is negative 7, and then 0 times 4 is 0, so you end up with negative 7 plus 0 plus 0. And then 0 plus 2 plus 0, because 0 times 5 is 0, 1 times 2 is 2, and 0 times 6 is 0. 0 times negative 7 is 0, plus 4 plus 0. 0 plus 0 plus 6, and then 0 plus 0 plus negative 8. End up with 5, 2, 6, negative 7, 4, negative 8. Okay? So, for this one, this is the identity for all 2 by 2 matrices. Actually, it would be the identity for all n by 2 matrices, I guess. But whatever. If I were to want to find the identity for the other side, remember I said last time that for 2 matrices, A times B is not equal to B times A. So I would need a different identity matrix for the other side so that the multiplication would work. And in the book, if you look at the example on page 485, it actually says that the identity is going to have to be 1, 0, 0, 1. It's going to have to be this. If I were to multiply on this side, this with this, I would get back this. But I could not multiply this with this on the other side. It wouldn't work out. It wouldn't make sense. Kind of what we ran into last time. So that's the idea behind the matrix identity, the multiplicative identity for matrices. So let's go back to numbers again, right? The additive identity of the real numbers is 0. So given any number a, how do I get it? When I mean it, I mean how do I get 0? Well, I just add the opposite, right? So a plus, and I stick a little dash there, a negative sign, right? And I'll get 0. So 5 plus what equals 0? Obviously negative 5, right? The answer is negative 5. So this is something I would call the additive inverse. And again, it just seemed like at the time it was overcomplicating things. Please, let me just do the work, get my grade, and move on. Why do I need to call it anything? And now it's starting to become important. The multiplicative identity, as we just saw, of the reals is 1. How do I get it given any number? So if I have a times something has to equal 1, well, we don't realize we're thinking this way, but really what we do is we just take this number and put it in the denominator and write a 1 on top. So a times 1 over a would give me 1, right? These cancel. So 5 times 1 over 5 is equal to 1. Another way that we would write this is we would write 5 with a little negative 1 there, right? And then we knew that meant you flip it. So this is kind of the notation we're going to use from now on with a little negative 1 symbol. So 5 negative 1, or 1/5, is the multiplicative inverse, or let's just say the inverse of 5 for now. So what is the multiplicative identity of n by n matrices? That's 1. That's a 1 with a bunch of zeros. Ones on the diagonal and zeros everywhere else. Now, let's say I'm given a matrix, just like here. I was given a number, and 1's on the other side of the equation. I need to figure out the number that when I multiply will give me 1. That's the thing that we called the inverse, right? So let's say I'm given a matrix 1, 2, 3, 4, 5, 6, 7, 8, and 9. And I want to end up with 1, 0, 0, 0, 1, 0, 0, 0, 1 when I'm done doing this multiplication. This thing is the inverse matrix. And it only exists for square matrices. So only for n by n matrices. And really the identity only exists for n by n matrices. This example down here, there is no identity for both the left and right sides. There's this identity here, which I guess might be called the left identity, and this might be called the right identity. But there's no one matrix that works for both sides. It has to be a square matrix like this one, so that when this matrix, if I multiply it on either side, I'll just get back what I started with, the 3, negative 5, 4, and 6. So a big question that if you go into the right field, you might spend the rest of your life finding efficient ways of doing this, and that is, how do I get the inverse? See, to get the inverse of a number, it was easy. I just flip it, the multiplicative inverse. But how do you get the inverse matrix? In this course, we might learn one or two ways, but depending on the size of the matrix, and in the business or finance world, there's it's a very important field of study is how to find the inverse of a matrix, how to compute the inverse, because you'll have to solve very large systems of equations, and you can write up codes that will do it, but does the code do it quickly? is the big issue. So we know how to do it, but now the question is how fast can you do it? So that's the idea. So there are many ways. One way that we'll learn later is called using the determinant and the adjoint. Something called the adjoint. We'll learn what these are later. And really, this is a fast way, as far as this course is concerned. This is fast for 2 by 2 matrices. Um, when you're doing it by hand, because the determinant's really easy to compute for 2 by 2 matrices. For 3 by 3, it becomes a little bit more involved in general. So the other way, I don't even know what you call it, but it's this way where you basically write the matrix that you're dealing with on one side, and then you have an augmented matrix altogether, and then you'll write the identity matrix on the other side. And then you do a bunch of row operations to both sides. So whatever I do here, kind of like a regular equation. But these are row operations now. So whatever row operation I do on this side, I do it on this side. And then you try to get this side to be the identity. So the goal is you get this side to be the identity, and whatever you end up with on this side after all your row operations are done, this will be your A inverse, right? So this is kind of a very organized way of doing it. It's long, it's tedious, but it really is good to start finding your inverses this way so you could see what they mean. And what they will mean is all of that work that you had to do in order to get everything in the Gauss-Jordan, what was it called? Reduced row echelon form. All of that work is contained right here in the inverse. And so all you have to do is a matrix multiplication, and you're done solving the problem. And that's the significance of that. So, all right, again, just like the rest of math, I can talk and talk and talk, but best way to learn it is to do it. So we will do it. Example 2, and this is on page 488. All right, so I'm given this matrix and I want to find the inverse. And this is not the easiest problem to start with because it's 3 by 3 matrix, but it's doable. So what I need is I need A inverse, whatever it is, whatever it looks like, to cancel out A, so that when I multiply them, I end up with the identity, right? So I need this thing to times A inverse to give me 1, 0, 0, 0, 1, 0, 0, 0, 1, right? Well, from this, the book goes into more detail, and it's a lot of writing, but the book goes into more detail on page 488, and it kind of explains the logic of how, of a faster way, and why we write it like this. 1, 0, 2, negative 1, 2, 3, 1, negative 1, 0. So this is just A all over again. And then you kind of write an augmented matrix, but instead of just writing one vertical line, you're going to write the identity matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. And the reason we're doing that is because I need three different things to be happening at the same time. I need three different equations I need this equation. How do I explain this? I'm sorry. If I were to write out A inverse as something like A11, A12, A13, A21, A22, A23, and so on, write out all the coordinates or the elements, and I were to do the multiplication, I would get a system of equations stating three things. And that's really what this is doing here. This is a system this is an augmented matrix saying those three things all at one time. I hope that was confusing because it sounded like it. Okay, so the goal is, again, to get this, we want to get this so that on the left-hand side we have the identity matrix, and that's it. Let's that be our goal. So we want to get this into reduced row echelon form. All right. So what's one thing we can do? We can multiply the first row by -2 and add it to row 3. All right. So let's do that. And we'll get 1, -1, 1, right? We don't change anything else but row 3. And then we end up here with 1, 0, 0, 0, 1, 0. And whatever you do to one side, we do to the other. So now we're going to take the first row here, multiply it by -2, and add it to row 3. So we end up with -2, 0, 1. Okay? First step. Second step, let's just add together row 2 and row 1 and see what we get. Or how about we don't? How about we just multiply row 2 by a half? So then we'll do 1, -1, 1, 0, 1, and -1/2, and then 0, 5, and -2. Whatever we do to one side, we do to the other. So this becomes 1/2, and then we just copy down everything else. Okay, now let's add together row 2 and row 1. And we'll end up with 1, 0, 1/2, and that's the only thing that changes, so everything else is just 0, 1, -1/2, 0, hold up. Oh yeah, 0, 5, and -2. And then this is 1, 1/2, and 0, 0, 1/2, and 0, -2, 0, and 1. All right, now let us multiply row 2 by -5 and add it to row 3. And we get 1, 0, and a half, 0, 1, and -1/2, and then 0, 0, and 1/2. All right, whatever we do to one side, and then so this becomes -2, -5/2, and 1. All right, the goal is to try to fit it on one page. Let's multiply the row 3 by 2, and we'll get 1, 0, 1/2, 0, 1, -1/2, 0, 0, 1, and then 1, 1/2, 0, 0, 1/2, 0, and then -4, -5, and 2. Okay, so to save space, we'll do 2 steps in one. We'll take the third row, multiply it by -1/2, add it to the first row. Then we'll take the third row, multiply it by a half, and add it to the second row. And we will get 1, 0, 0, 0, 1, 0, and 0, 0, 1. And then we'll have here 3, 3, -1, -2, -2, 1, -4, -5, and 2. Okay? So here we have the identity, and you're going to have to just trust me on this and believe that this is a inverse. and believe that we did everything we did got us there. And in fact, I guess you don't really have to just trust me. What you can do is you can say, okay, if I take this matrix here and I multiply it by A, which was all the way up here, if I multiply this and this, I'll get the identity. So now, again, there's faster ways of doing this. This is just a way that we do it because we're learning it, and we want to kind of see what's going on in order to get it. But there's much quicker ways of computing the inverse. Um, but what it means is that if I can find the inverse quickly, and I have um, a, a linear equality that I want to solve, or really what's a more important problem is an inequality, but that's okay. We're not gonna. That's the linear programming part that we didn't go into yet. If I want to solve this, and I have the inverse, I can just in one step multiply these two things. Whoops, on the other side, and then I'll get A inverse times A. This is the identity, right? So A inverse times A gives me the identity matrix times whatever this thing is, X, which I don't know yet. And this is, we'll call this B prime, whatever it is. But the identity times any matrix is just that matrix all over again. So what you end up with is you end up with your solution. This actually solves your problem. So yeah, that's what the identity does. Okay, let's just keep doing more problems, Mr. Rodriguez. All right, so example 3. That's pretty hard. If I were to give you something like a 4 by 4 matrix to find the inverse of, I mean, you saw it took a whole page to do it for a 3 by 3, and it's not necessarily difficult. It's just very tedious, and that can get frustrating. So I wouldn't be a very nice person to give you something like a 4 by 4. So if I did, there's going to be a trick somewhere. Just be aware of that. Okay, so example 3. So we have A is equal to 4, -6, -1, and 2, and we want to find A inverse. So let's kind of do the same thing again. 4, -6, -1, and 2. And then we write over here 1, 0, 0, 1. Right? So let us multiply the first row by a fourth and see what we get. Well, we get 1, -1 fourth, -6 and 2, and on the other side we get 1/4, 0, 0, 1. Let's multiply this first row by 6 and add it to the second row. First row we don't change, but the second row, this goes away because 6 times 1 plus -6 is going to give me 0. And then this ends up being 2. So we end up with 1/4, 0, 3 halves, and 1. Okay, and another step, let us multiply the second row by 2 and see what we get. We get 1, -1/4, and then 0, 4. I'm sorry. Am I crazy? Oh, this should be a 1/2. I apologize. No, this should be a 2. This should be a 1/2. Right. Okay, and then we multiply the second row by 2 and we get 1 here. So we get 1/4, 0, 3, and 2. And then finally, we'll multiply the second row by 1/4 and add it to the first row. And we get 1, 0, 0, 1, and then 1, 1/2, 3, and 2. Okay, so this is the identity, this is A inverse. And here, let's go ahead and test it so that you can see I'm not crazy. I'm claiming that A times A inverse down the road is going to give me I. So we have 4, -6, -1, and 2, and then I multiply this thing, 1, 1/2, 3, and 2. Let's see what I get. 4 times 1 is 4. 1 times 3 is -3, so I add those together and I get 1. 4 times 1/2 is 2. -1 times 2 is -2. I add those together, I get 0. -6 times 1 is -6. 2 times 3 is 6. I add those together, I get 0. -6 times 1/2 is -3. 2 times 2 times, oh, sorry. -6 times 1/2 is -3. 2 times 2 is 4, so this ends up being 1. I'm sorry. Yeah, so that is the identity. So that's this is the inverse. All right, and so you see a lot of work goes into finding it, and then on the calculators, there's a button that can be pushed, and you just it'll do it automatically for you. All you got to do is enter in the numbers, and you just do something like it's very obvious how to do it, but I want to make a video, like I've said, about what the calculator can do, because there's a lot of neat theory here. If you can step back away from the arithmetic and see what this is capable of doing, and start thinking on a little bit of a bigger level, you can solve some very interesting problems, and then let the computer do the arithmetic. That's the point. The point of math isn't to sit down and crunch numbers all day. It's to think of how to solve problems, and then maybe find an efficient way to compute the solution. And now that we have computers, they can do all that. Okay, so let's see. That's pretty much it. I'll do one more. I'll do number 19 from the homework. Find the inverse 0, -1, 1, and 4. Right? So let me go ahead and do my thing here. 0, -1, 1, and 4. 1, 0, 0, 1. So first thing is, let me go ahead and switch the first two rows, or the only two rows. 1, 4, 0, -1. And then this, I have to switch these two rows, 0, 1, 1, and 0. Okay? Then I'll do 4 times the second row plus the first row. So I'll end up with a 0 there, because this will become a -4. And I copy down the second row and leave it alone. 4 times the second row here is going to give me a 4 there, a 1 here, 1, and 0. And then finally I'll multiply the second row by -1. And I'll get 1, 0, 0, 1, 4, 1, -1, 0. Okay, so I'm claiming that this is my inverse. And let's try it. This is my A up here. So A times A inverse is 0, 1, -1, 4, 4, 1, -1, 0. Well, this and this, 0 times 4 is 0, -1 times -1 is 1. This and this give me 0 times 1 is 0, -1 times 0 is 0. This and this, 1 times 4 is 4, 4 times -1 is -4, add them together I get 0, and then here I get 1. Alright, that's basically the whole section, and it's worth the whole section because it's a lot of work to find the inverse. I hope you enjoy it.